Hello everyone, welcome to the second video in this tutorial series. In the first video, we studied the interactions of a ligand in a pocket on the SARS-CoV-2 helicase at the C-terminus B site. In this session, we're going to be taking that same ligand and we're going to be docking it so that we can compare the docking scores and the resulting conformations against the known crystal structure. And the reason we're going to do this is because this means that when we generate those scores and those binding modes, we can compare those to the crystal structure and we can see how accurate the calculated binding score is and those poses to the crystal structure, which means that it gives us a sense of reliability in our results from our docking calculations. So essentially, we're just creating a baseline from which we can improve the binding affinity or the calculated binding affinity using Vena. So the first step is to open up the PDB structure of our protein with the ligand, which we saved earlier. So just going to fetch that now. Okay, so here's our protein. Here's our pocket and here is our ligand that we're interested in. So what we're going to have to do is we're going to save each of these as a separate mol2 file. That is the ligand and the protein. And so the first thing we're going to do is delete the ligand. So select residue, and then I'm going to click on the ligand, which has now been highlighted in green because I've selected it. Actions, atom and bonds, and delete. So now we're just left with the protein. Okay. And so now we've just got the protein. What I'm going to do is I'm going to dock prep this protein. So prepare it for docking, essentially. And that's just things like adding hydrogens, adding charges, just to make sure that the docking scores are representative of the structure. So we're going to Tools, Surface Binding Analysis, and Dock Prep. And it's selected model 0, which is the protein. It's going to ask us if we want to delete solvents and non-complex ions. So in this particular instance, we could do that. It's not particularly important, but since our site doesn't include any phosphates or waters or zincs, this shouldn't affect the binding score. But I'm just going to leave them in there for now. I'm also going to change any non-standard residues, so like selenomethionine, to the standard counterparts. Also going to incomplete any missing side chains from this known library. We're going to add the hydrogens, add charges, and write a mol2 file. Okay. So apologies, I'm just making sure that you can see my screen. Okay. There we go. I'll run through that procedure again because you may have missed some of that. So all I'm doing is Tools, Surface Binding Analysis, Dock Prep. Okay, there we go. So you should be able to see that now. So apologies there. Right, so I've selected the protein. I'm not going to delete the solvents. I'm going to change the non-standard residues for the standard ones, add the hydrogens and the charges, and write a mol2 file and incomplete any side chains. So it's okay. Do we want to consider each model in isolation from all others? Well, yes, we only have one model. Add hydrogens, we can have steric only or hydrogen bonding. So in this instance, we're going to include the hydrogen bonding because that's important to the structure of the protein. And we're going to keep the proteination states at histidine. Okay. Just press OK, and it'll run those calculations. So now you can see it's added the hydrogens to any residues, and it's factored in the hydrogen bonding there. Now we're going to add the charges to the protein. So this should add charges to the residual, the non-standard residues, so the phosphates and zincs. So phosphates set a -3 charge and zincs are at +2. This isn't hugely important because again, our pocket is quite far away from these two sites. But I'm gonna do it for just to be accurate. Okay, so just press OK, and it will run those charge calculations. And now it wants to save. It's going to save that. Okay, so once that calculation's run, you'll get this window pop up, and I'm just going to save this as protein doc prepped. Okay, so that was a mol2 file, and save. Okay, so now we've doc prepped our protein for docking. Now we need to do the same for the ligand. So what you can do is you can go back separately. So before we did the doc prep, when you had the protein, the ligand, you essentially do the same procedure, except rather than selecting selecting the ligand and deleting that, you select the protein. And to do that, you're going to select structure protein, and that will select the protein but not the ligand, and you can delete that and then run through the same procedure of doc prepping afterwards. Or what you can do is you can just save the undoc prepped ligand as a PDB file. Okay, and that's what I've done previously. So I did the same procedure that I just done for the protein, but for the ligand. And so if I go into File, Open, and Ligand, PDB, it's just popped in the ligand PDB file. Okay, so it's the exact same procedure that you just did for the protein, but rather than selecting the ligand and deleting that, you're selecting the protein and deleting that and keeping the ligand. Okay, so now what we're going to do is we are going to doc prep the ligand. So Tools, Surface Binding Analysis, and doc prep. And we just want to do the ligand, which is model 1, and you can tell that's model 1 just by hovering the mouse over. Okay, these don't apply because we're not dealing with a protein here, we're dealing with a fragment. We don't need to add incomplete side chains, add hydrogens, yes, add charges, yes, and write mol2 file. Okay, so we want to add hydrogens. Now, I'm not going to consider hydrogen bonding here because it will look at hydrogen bonding between the ligand and the protein, and that means that the calculation won't run correctly. So we're just going to consider steric hydrogens, okay, which is fine because when we run the docking procedure, it will calculate hydrogen bonding between the protein and the ligand. So steric only is perfectly acceptable for fragments or small molecules. Okay, and we're going to consider each model in isolation from all others. So okay, it's now added the hydrogens to our molecule. Now we're going to do the same with the charges. So okay, and it's given it a protonation state of +1, and this is fine. So this is again the ammonium that's being protonated, and what you can do is you can go in, if you're not unsure of the protonation state, you could use something like Marvin sketch to calculate the pKa, and you can create a microspecies plot to show you the predominant species at that pKa, and that's what I did beforehand to show that about pH 7 this will be about 60% protonated, so it exists in equilibrium. So we're going to keep it as protonated. I will do a separate video on the use of Marvin sketch for calculating protonation states, because it is quite useful when you're unsure of whether your molecule is charged or not, or protonated or not. Okay, so charge +1, okay. And now it's running that charge calculation. Okay, so now we have our ligand doc prepped. So I'm going to save that as ligand doc prepped mol2. And we only want to save our ligand. So just going to select that one. I'll save it relative to the protein, just so it stays in its location. And we've got ligand doc prepped mol2. Okay, so save. Okay, brilliant. So now we have doc prepped our protein and we have doc prepped our ligand. So now we're going to dock them in Vena. So to do this, we're going to Tools, Surface Binding Analysis, AutoDock Vina. So AutoDock Vina comes as a separate plugin for Chimera. It's free to download. Doesn't take very long to download at all. And I will include the link to both UCSF Chimera and to AutoDock Vina in the description below this video. So we've opened Vena, which I will share now so you can see. And what I'm going to do is I'm just going to put this to the side so that we can keep that window visible. Okay, so the first thing we need to do is to set an output file. So this is where the results of our docking will end up on our hard drive. So output file, we'll go browse. And I've already created a folder for this called docking scores. And I will just call that docking results and set output location. I'm going to overwrite my previous one. So the receptor is the protein, so that's model 0, and the ligand is our small molecule, in this case our fragment, which is model 1. Now, what we have to do is to define our search area, or what is called in docking is known as the grid. So the grid is essentially the three-dimensional space within which your calculation, your binding affinity calculation will run. And so you can define that by drawing it, or you can place coordinates in. I prefer to draw it because it's a little bit easier. So I'm going to click resize search volume, and then how you choose to do this is up to you. I prefer to do button 3, so my right click mouse. And what I'm just going to do is I'm going to go over my pocket where I think my molecule is binding, right click and drag. And you'll see it's created a search grid. Okay, so that's this green box. So when I run my Vena calculation, it will test all the conformations and the binding affinity scores within this box, but not outside this box. Okay, so obviously the larger the box, the larger the search space. So the larger the number of calculations it has to run, and so the longer that will take. So if you're completely unsure of where your molecule binds to the protein, you could draw this grid over, say, the entire protein, like that. You can change the shape just by grabbing the faces. However, that does mean the calculations will take a long time, and the accuracy may drop because these things aren't always completely accurate. So if you have a defined idea of where your molecule binds, then that helps enormously with the accuracy of the calculations. So luckily for us, we know that this fragment binds in this pocket because that's a crystal structure. It's based on a PDB structure. So what I'm going to do is just confine the size of that grid to around that pocket. Okay, so we're just to the right of the ATP site on the Rec A2 domain. And I'm just bringing that grid in a bit just to make sure that we're only searching inside the desired pocket. Okay, so just going to visually inspect it, just rotate it around a bit. Just move it around. And I think I'm quite happy with that. Okay, yeah, looks good. So an important thing to note here is that if you're planning to use this as, say, a baseline for further calculations. So what I mean by that is if this is your starting point, say you're doing some fragment growing or you're docking some molecules in the same pocket, which is what I'm doing in my case currently, is that you have to keep the grid size the same, because if you're going to dock other molecules into the same area or the same pocket and you want to test if they will bind into that pocket, you want to reduce the number of variables in your calculations. So for example, using the same doc prepped mol2 file, the protein, and most importantly, making sure that the grid size is the same, because if you expand that search area, for example, it's going to start running calculations outside of that search area. So you're going to get other results beyond what you would if you just had the same size grid that you had before. So in terms of reliability and reproducibility, you want to keep that that grid the same, ideally, if you're planning on using, say, this fragment as a baseline. Okay, so to make sure you keep it the same, the coordinates are given to you here when you draw it. So next time you come to run this, you could type them in manually, or you could draw it and then you can just type them in to kind of fine tune it. Okay, so we have our grid, we have our small molecule, and we have our protein, both of which have been doc prepped. So I'm going to check the receptor options, and these are all fine. So these are all true. It's ignoring the waters. That's not important for us because there's no water in our pocket. If I was doing it in the ATP site, then maybe I would include them, because obviously the phosphates and the waters are involved in hydrogen bonding along with the residues, but for this pocket, it's not important. Okay, and going to ignore, we don't want to ignore all standard residues because they may be important somewhere for binding, obviously for the shape of the protein. So then what we're going to do is check the ligand options. So it's going to merge charges and remove non-polar hydrogens, and merge charges and remove lone pairs. So both of those are true. In the advanced options, it gives you a number of binding modes. So this is essentially how many different conformations do you want to see as a result of this calculation. So by selecting 10 binding modes, it will show me the 10 lowest scoring binding modes from this calculation. So the exhaustiveness of the search essentially is how long the calculation will take. So it will explore more conformations, more binding modes. It means your calculation will take longer, but it should be more accurate. So I tend to leave that, as long as it's nothing too overly complicated. You know, if this was a huge macromolecule, then I may want to consider reducing the exhaustiveness a bit, just for saving time. But because we're dealing with a fragment here, I'm quite happy to leave that at the maximum. And the energy difference, so it's given 3 kilocalories per mole, and so that's the highest energy difference between each of the conformations. And I tend to leave this as high as possible as well, because what it means is that if you docked this molecule and the 10 lowest scoring binding modes were all very, very similar to each other, so essentially they're binding, say, right on the edge of this pocket with this phenyl ring just slightly rotated, then that's not very useful for me, because I know that it binds within the pocket, but the calculation may say that this is the lowest scoring area, which isn't ideal when I know that's probably not true just based on the crystal structure. Okay, and then finally, the executable location will be the downloaded AutoDock Vina file from scripts, which will be saved onto your hard drive once you download it. Okay, So I am happy with everything here, and I'm now going to dock this molecule into this protein by pressing OK. Okay, so you can see it's running down in the bottom left corner. It's telling us that the calculation is running. So we've just got to wait for it to finish. And there we go. We've got the scores now. So okay, so you can see the scores. And if we scroll down, so if we click on here and scroll down, it will show us each of those binding modes associated with that score. And so the green is our calculated binding affinity, and our blue is our crystal structure, because that's the one that we loaded in. Okay, so if I take a look at the let me just move this here. So this is the lowest energy binding affinity. So it's giving us a score of minus 5.2, which is the calculated Gibbs free energy. And as we can see from the crystal structure, they're pretty close. So we have this parafluorophenyl ring in the pocket, very close to the crystal structure. We have this amide bond here, and with a carbonyl towards this arginine residue. And there's just a bit of contortion between around this bond where where this ammonium and amide hydrogen are kind of close to each other. Okay, so given that the resolution of the crystal structures is about 1.9 angstroms, I think, from this paper, that's pretty much kind of as good as you can hope to get, because what you've got to remember is that the crystal structure is essentially a snapshot of the molecule in the pocket, but in reality this molecule is moving around in this pocket. It's it's got rotatable bonds, and it can vibrate and etc etc. So this is a pretty good score and pretty good binding mode. Okay, so we can scroll down as well. So if we click back on the Vena here and we scroll down, we can see these two are pretty close, and some of the others are still reasonable. I mean, it's still within that pocket. It's just kind of moving around a bit, which isn't surprising given that this is a fragment, so the binding interactions will probably be quite weak. So we would expect it to move around a fair bit. Okay, whereas if this had multiple binding interactions with the protein, then it wouldn't move maybe so much, and so we wouldn't see quite as much variation in the binding modes. Okay, so that is great. We now have our docking scores. And what I'm now going to do is I'm going to save these docking scores as a PDB file so that we can study the interactions a bit more carefully. So I'm going to go to File, Save PDB, and I'm just going to call this docking results, binding modes, PDB. And I'm just going to save that. Save that as a PDB file. Okay. So now we want to have a look at those interactions and see how closely they line up with what we had last time. Okay. So now what I'm going to do is go into BioVia, Discovery Studio. Okay, so we're back in this program again, and what I'm going to do is File and Open, and I'm just going to open the docking scores, so the PDB file that we just saved. Okay, and so you can see here that what we have is our protein, a lot of solvent molecules, which we won't be concerned with, and all our binding modes, which are now kind of overlapped. So rather than being nicely stacked, so we can look at them one at a time, they're all now overlapped, which isn't very useful for us because it's a bit cluttered, but we're going to sort that out now. So first thing I'm going to do is I'm going to get rid of the water molecules because they're a bit of a distraction. So scripts, visualization, hide waters. So it's just hidden all those waters for us. Now what we're going to do is go to receptor ligand interactions, which we've already selected. And I just want to focus on the binding interactions. So I'm not concerned with the rest of the protein. I'm just concerned with the binding interactions. So what we can do is if we go to step through ligands and just click down here, it will go down. So we just have one, and then what I'll do is I'll jump back up to the top one. Okay, so I think this is our original crystal structure here. And so yeah, so that one there is our original crystal structure, because we saved it. We saved the whole file as the PDB, so we didn't just save the binding modes, we saved our original undocked one. So that's quite useful because it means we can directly compare the binding modes here. Okay, so what I'm going to do is first of all, I want to get the ligand interactions. So now I'm just going to click on ligand interactions. And now it's just got rid of the rest of the protein, and it's just showing us the direct ligand interactions. Now this looks a little bit odd because all we can see is the amino acid residues and our molecule. So what I'm going to do is I want to show the surface of the protein just so I can see the shape of the pocket. So for example, if I just want the hydrophobic surface, I'm just going to click on hydrophobic, and now we can see the shape of the pocket, which is nice. I'm going to expand that a little bit, so just press expand just so we can see sort of around kind of the entirety of the pocket. Now what I'm going to do is I want to know what residues we are interacting with here. So I'm going to right click just anywhere. I'm going to go to labels, add. Just want to make sure that you can see. Yeah, you should be able to see that. So right click, labels, add, amino acid. So I want to know what amino acid is interacting here, and attribute. This is personal preference. I like 3-letter and ID because that gives you the 3-letter code and what number residue you're looking at bonding with. So I click that one and press apply. And so now it's given us the labels on the residues that are interacting with the ligand. And now what I want to do is I want to know what kind of interactions these are, because that will be helpful for us. So I can go on to interaction options, and I can say show distance. So how many angstroms away are these atoms from each other? How long are those bonds? And I also want to know what type. So I click show type. Okay, and now it's showing us a lot of information here. So it's giving us the residues that are interacting with our ligand. it's telling us the distance between the atoms, so how long those bonding interactions are. And it's telling us the kind of interactions that we are looking at. So here we're looking at a conventional hydrogen bond. Here we're looking at a carbonyl hydrogen bond interaction. There's a standard hydrogen bonding interaction here. This one is saying it's a donor-donor interaction, which is unfavored, which is why it's in red. So that's potential issue, but this may be why when we calculated the docking, why we saw the rotation of this part here, because maybe that's repelling away from there. And of course, this is an equilibrium, so when this is unprotonated, then it will form a hydrogen bond potentially with this NH over here on this residue 503. Okay, so if we look down in the pocket, we've got a pi cation interaction between the arginine and this fluoropyridine. A pi alkyl interaction here, which is a bit longer, so maybe that's a bit of a weaker interaction. 5.2 angstroms versus 3.2 angstroms, so you could argue the pi cation is more important. There's a hydrogen fluorine hydrogen bond down there, and so lots of useful information here, and we can kind of rotate around the back of the pocket as well, just look at the residues. Okay, and we can also, if we wanted to make this look a bit nicer, we can go into scripts, visualization. Okay, we'll talk through this later. Okay, so now I want to look at the ones that I've docked. So this is the crystal structure, but I want to look at the ones that I've docked. Okay, so I'll just click down, and now it's showing me the interactions for our lowest energy conformer. So again, pi alkyl and pi cation, and conventional hydrogen bonding here. So this is the donor-donor clashing that I was talking about. So you can see that this ammonium and this nitrogen don't want to be near each other, but obviously this is an equilibrium, so that bond will probably rotate. There's a pi cation interaction here between this residue. So that's not come up as labeled. So if I right click, labels, add amino acids, apply, there we go. So now it's given us that one. So this one wasn't being recorded as being important for the binding in the crystal structure, but in our dock structure, this phenylaniline 472 residue is saying that it's doing pi cation interaction with this ammonium. And the possible reason for that is because in the original crystal structure, there was no proton on this amine. So when it's crystallized, maybe it was in its neutral state, just based on the pH. So then this interaction maybe didn't exist when the crystal structure was captured. Okay, so here we've got conventional hydrogen bonding with this arginine residue, so that looks quite important. They're fairly small bond lengths, around 2.2 to 2.6 angstroms. We've got a pi cation again. We've got a fluorine hydrogen bond and a pi alkyl. Okay, so that's interesting for us. Good to know. And if we go back, we can compare those sort of by flicking back between them, just to see which residues are important in this instance and our docked scores. So you'll notice that just by adding the charge to that that ammonium, the interactions that were going on over here in the crystal structure, so the 502 and 503 residues, they were formerly hydrogen bonding. And in this dot structure, they're not. And so again, this is because we're looking at snapshots. So in reality, this molecule is probably kind of flipping back and forth between these two conformations. And both of those interactions are probably important for keeping the compound in the pocket. So so that probably locks it into place a bit more because you've got more hydrogen bonding here. Okay, we can go through the rest of these. So if we just scroll down, we can see the next lowest binding mode is just a slightly distorted version. This one is a bit more different. So, we've still got this pi-cation interaction, but now the hydrogen bonding is happening up here. And this residue, which is residue 591, is now interacting via conventional hydrogen bonding and a potential salt bridge as well. So a charge interaction. Okay, so that's plausible again, but it's different to our crystal structure. Now remember as well that because we're looking at a fragment, it's likely that any of these are plausible because this fragment can move around a lot because these interactions aren't too strong. Okay. And then we could scroll through the rest of these if we wanted to. So there's a pi sigma interaction here, which we didn't have before. There's this conventional hydrogen bonding between the ammonium and the carbonyl of residue 503, which is important, but we'll notice that the in order to make that interaction, the fluoropyridine has had to move out of the pocket a bit more compared to that earlier pose and compared to the crystal structure. So that tells us some useful information because then maybe, if we want to exploit this hydrogen bond, then we could think about extending this molecule so that the fluoropyridine stays in here, keeps all those interactions, but now we're forming an additional hydrogen bond down here. So we're increasing that binding affinity, and that's something that we'll look at when we come to designing some compounds. Okay, and then obviously like last time, we can look at different surfaces. So we can look at the charged surface here if we wanted to, or the aromatic or the hydrogen bonding surface. So hydrogen bonding is useful if you wanted to know, where to install hydrogen bond donors and acceptors. Okay, so we've got an acceptor here and we've got a donor here. So if we could install a hydrogen bond acceptor here, then that might help our binding affinity. Okay, so I'm just going to keep it as the hydrophobic for now. And I'm just going to create a 2D diagram here so we can look at the interactions in 2 dimensions. So we've got this arginine, this leucine, and some other interactions here. Okay, so in this video, we have docked our fragment back into its original pocket. We've compared the binding scores, and we have looked at the specific interactions, both with the crystallized fragment and with other binding modes. And looking at those other binding modes gives us information about how we could potentially use some structure-based drug design. So what other interactions we could look at trying to exploit by designing compounds that will match those interactions. Okay, so thanks very much for watching this video, and in the next video we'll be looking at, rather than docking a known compound, we'll be looking at doing some structure-based drug design. So we'll be looking at designing our own compounds, docking them using the same procedure we've used this time, and then using Discovery Studio Visualizer to look at the interactions and see if we can improve the score in Vena, but also if that score is reflected by new interactions that we weren't previously forming in this fragment structure here. Okay, so thank you very much for watching, and I'll catch you in the next video.